All right, today we're going to dive in and unlock the story of how machines learn to understand something that's totally fundamental to language: sequence. This is really the story of an idea that gave AI a memory, and it all kicks off with a pretty simple question. So just look at these two sentences. They've got the exact same words, right? But the order completely flips the meaning. One is, just a regular news story. The other one, well, that's the headline. The problem was, early AI models just saw a bag of words. They completely missed this crucial context. To them, these two sentences were exactly the same. So the big challenge was, how do you teach a machine that order actually matters? Well, the solution really starts with tasks like this one, part of speech tagging. It's all about labeling each word with its grammatical role. Think about the word book. Is it a noun, like in I'm going to read a book? Or is it a verb, like we need to book a flight? To get that right, the model has to understand the sequence, the words around it, not just the word itself. And this really gets to the heart of the problem. As humans, we do this stuff intuitively. If you see the word the, you're not expecting a verb to come next, right? You're automatically waiting for a noun or an adjective. The goal was to build an AI that could learn these exact same patterns, one that could use the past to predict what's coming next. And that's where the first hero of our story comes in, the Recurrent Neural Network, or what everybody calls an RNN. This was a whole new kind of architecture, designed from the ground up specifically to handle sequences. So the huge idea behind an RNN is that it doesn't just look at one word at a time, all by itself. Each part of the network, which we call a cell, takes in a new word, but, and this is the important part, it also gets information from the cell that just processed the word before it. It has a direct connection to its own past. Here's kind of how that flow works. At every step, a new input, a word, comes into the cell. But at the exact same time, a state vector also arrives from the previous cell. Now, you should think of this state vector as the network's working memory. The cell combines the new word with this memory, updates it into a new memory, and then passes that new, updated memory along to the very next cell in the chain. Okay, so this sounds amazing, right? A network with a memory. But this first hero had a pretty critical flaw. While the idea of a flowing memory was absolutely brilliant, in practice, that memory turned out to be incredibly short-term. It suffered from a little something called the vanishing gradient problem. It's a lot like a whisper in a long game of telephone. You know how that works? The information from the very first word in a sentence has to be passed through every single cell to reach the end. And with each step, with each pass, that signal gets a little bit weaker, a little more garbled, until eventually the original message is just completely gone. Now, you don't need to be a math genius to get why this happens. To pass its memory along, the network has to multiply it by a bunch of numbers over and over again. But just think about it. When you keep multiplying numbers that are less than 1, the result just gets smaller and smaller and smaller until it basically vanishes. The memory literally fades away to nothing. So, how do you fix a fading memory? Well, you give it a really ingenious upgrade. This solution was called the Long Short-Term Memory Network, or LSTM. And this was a total game changer. LSTMs tackled the problem by changing the whole operation at its core. Instead of that multiplicative chain that just kept weakening the signal, it introduced what you can think of as an additive conveyor belt. Information can now be placed on this belt and travel all the way down the sequence without degrading. And the key to this whole thing was a set of smart neural gates that controlled exactly what got on and off that belt. These gates gave the LSTM incredible control over its own memory. First up, you have the forget gate. It looks at old information on the conveyor belt and decides if any of it's no longer relevant and should be tossed out. Next, the input gate looks at the new word coming in and decides what new information is actually important enough to add to the belt. And finally, the output gate determines what part of the memory is useful for the task at hand. The most crucial part is this: the network literally learned how to manage its own memory. So with LSTMs, we finally had a really powerful model with a reliable long-term memory. Awesome, right? But there was still one more kind of subtle challenge to deal with. See, even with a great memory, the model was still processing everything word by word, from left to right. And sometimes that can lead you straight down the wrong path. Take a look at this classic sentence. When you read "the old man," your brain almost certainly jumps to the conclusion that man is a noun. An LSTM would do the exact same thing. But then you hit that second "the," and suddenly that interpretation makes zero sense. You have to backtrack in your head and realize, oh, man is actually the verb here, as in the elderly people are the ones manning the boat. So that's the dilemma. The LSTM made the most likely guess at each individual step, but that led to a result that was totally impossible for the sentence as a whole. And this raised one final, really crucial question. How could we teach a model to look at the entire sequence of guesses and pick the one path that makes the most sense overall? The answer was to add one more layer right on top, a conditional random field, or a CRF. Now, the easiest way to think of the CRF is as a kind of supervisor. The LSTM does its usual word-by-word analysis and suggests a few possible tags, and then the CRF steps in, looks at all the possible full-sentence combinations, and picks the single path that is the most grammatically coherent from start to finish. And here's what that looks like in practice. On the left, you've got the LSTM working alone. It makes its best guess at each word, confidently tagging man as a noun, and then it hits a wall, a grammatical error. But on the right, the CRF evaluates that entire path, sees that a noun followed by the is super unlikely, and just throws that whole path out. Instead, it chooses the path where man is a verb, which, of course, makes perfect sense for the sentence as a whole. So that's the journey. We went from a simple network with no memory at all to one that could remember, and finally to one that could see the whole big picture. And as you can imagine, this evolution had a massive, massive impact on natural language processing. Now, this didn't just happen overnight. The core ideas were actually developed over decades. It started way back with the first RNN in '86, followed by that crucial LSTM fix in '97. And then it was refined with CRFs in the 2010s, which led to LSTMs becoming the absolute go-to solution for pretty much every sequence problem for years. But even this powerful architecture still had its limits. The very nature of RNNs, the fact that they have to process one word at a time, makes them pretty slow and hard to run on modern parallel hardware like GPUs. And even with LSTMs, that long-term memory could still get a bit fuzzy on really, really long texts. And it was these limitations that actually paved the way for the next great leap in AI. And that leaves us with one final thought to chew on. This entire architecture we've just talked about is built on a memory of what came before. It's sequential by its very design. But what if a model didn't have to look back? What if it could look at the entire sentence, past, present, and future, all at the same time? Well, that very question is what led to the next revolution.